Hello everyone! In this tutorial we explain how to calculate areas of regions bounded by functions or curves. In particular, we consider this example. The example goes like this. Find the area of the region bounded by y is equal to x squared and y is equal to 2x minus x squared. These are two parabolas and we want to find the area of the region bounded by them. When you encounter these types of problems, the first step is to sketch a graph. However, to sketch the graph of the region, we first need to find the intersection points of these two parabolas. So let's do that. To find the intersection points, we actually need to solve a system of two equations. The first equation is y is equal to x squared, and the second equation is y is equal to 2x minus x squared. To solve this system of equations, we will simply write x squared is equal to 2x minus x squared. So we will have x squared is equal to 2x minus x squared. Now, what we can do over here, we can simply move this minus x squared to the left-hand side, so we have 2x squared, and we will have minus 2x if we move 2x from the right hand to the left hand side, and this should be equal to 0. Good. This is obviously a quadratic equation on the left hand side, and we need to find its zeros. In this case, the situation is easy. We can simply factor this quadratic equation like this: 2x, and over here we will have x minus 1. And this is equal to 0. Here it's obvious that zeros are x is equal to 0, and another 0 is x is equal to 1. And let's find the intersection point. This point x is equal to 0 correspond to the point y is equal to 0. How do I know that? Well, I can simply substitute this x equal to 0 in any of these equations, and y is 0. Consequently, the first intersection point is 0, 0. How about the second intersection point? Well, here we are going to take x is equal to 1 and substitute this value in any of these two equations. For example, if we substitute x is equal to 1 in the first equation, we have the second intersection point, which is x is 1 and y is 1. And that's it. Now we are ready to sketch the graph and to sketch the region. Let us sketch the graphs of these two functions and the region bounded by them. Here is my vertical axis, y, and here's my horizontal axis, x. Let's first of all denote the intersection point. The first intersection point is 0, 0, that is, it's the origin of our coordinate system. And the second intersection point is x is 1 and y is 1, and let us simply draw here a horizontal line, and let us draw here a vertical line, and the intersection is here. This is the point 1, 1. So let's denote it. Good. First of all, let's sketch this function. Y is equal to x squared. This function looks like this. It is parabola starting from 0, and it has this shape. On the other hand, let's sketch the function 2x minus x squared. To sketch this function, let's first of all find the zeros of this function. Obviously, the zeros of this function are x is equal to 0, and another 0 is x is equal to 2. And you can simply verify that by substituting x is equal to 2. You will have 4 minus 4, and that's 0. Consequently, if this is 1, this function will have 0 over here too. And consequently, it's going to look somehow like this. And here, we already know that the intersection point between these two functions is actually at 1, 1. And here it is. The maximum actually of the function y is equal to 2x minus x squared is going to be at this point. Here for clarity, let's use different colors to denote the two functions. This is our first function. And I'm trying to nicely follow this dashed line to make the graph more clear. So be patient over here. And this is y is equal to x squared. And let's use, for example, another color, for example, green, to denote this function. Y is equal to x minus x squared. And here it is. So let's use the green color. And here it is. Perfect. Let me now take this branch also. And here it is. And of course, this function will continue like this. And the region enclosed by these two functions is this region over here. And let's, for example, use blue color and let's sketch this region. Here is the region. We need to compute the area of this region. And let's not forget to write here that y is equal to 2x minus x squared. That is, we know that this is the function. Let us learn how to compute this area. There are several ways. Here's the first graphical approach. Namely, let's sketch this region over here. Here it is. Now, for certain value of x, let's denote this value as xi over here. We can construct a small rectangle. Here it is. This is a very small rectangle. That is, the width of this rectangle is small. And let's denote the width of this rectangle over here as delta xi. Now, obviously, this dimension over here, that is the height of this rectangle, is the upper function minus the lower function. That is, this height over here is 2xi minus xi squared minus the lower function, xi squared, and that's it. Consequently, this small area over here, and I'm going to denote it by AI, becomes, let's write it here, AI is, let's see, it's the height multiplied by the width, so it becomes 2xi, and what do we have over here? Minus 2xi squared multiplying delta xi. Now, this region can actually be computed, or better to say, and approximated as a sum of these small rectangles. Namely, we can construct a similar rectangle over here for certain xi, then over here we can do the same, and we can segment this whole region by these small rectangles, and then we can sum them together and we can approximate this area. Now, when delta xi actually approaches to 0, this whole sum of all these rectangles becomes an integral. All this implies that we can calculate the area A of this region over here. That is, we can calculate this area A as an integral from 0 to 1, upper function that is 2x minus x squared minus the lower function, and the lower function is x squared, and that's it. And here we have dx. Now, this integral becomes integral of 0, that is the bounds are from 0 to 1, and over here we will have 2x minus 2x squared dx. Good. Let's continue. Let's solve this integral. We have that area A is equal to. Now, we can integrate this term, then we can integrate this term. So let's do that. So let's write it over here. We have integral from 0 to 1. Over here we will have 2x dx. Then we will have minus integral from 0 to 1. Then we will have 2x squared dx. Next, this becomes, we can take 2 out of the first integral, and we have integral from 0 to 1 dx, and don't forget x here, minus an integral from, don't forget 2 over here, from 0 to 1 x squared dx. And let's compute, that is, let's compute these integrals. We have 2 multiplying, let's see what do we have here, x squared divided by 2, and the bounds are from 0 to 1. Then we have here minus 2 multiplying x to the power 3 divided by 3, and the bounds are from 0 to 1. And let's substitute these bounds. What do we have over here? We have 2 and 2 can be cancelled, so we have x squared, and the bounds from 0 to 1 simply become 1. And what do we have here? We have 2, and we have here the bounds are from 0 to 1, x to the power 3. This becomes only 1 over 3. And let's further simplify this. This becomes 1 minus 2 over 3, and finally this becomes 1 over 3. And that's our solution.